Hello, 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 everybody. Root Beer here with the very last question on the 2008 Fermat paper. Question 25 reads as follows. A right regular hexagonal prism is sliced as shown in the diagram. So they've come along and they've chopped it with a single slice. They sort of ran a plane through it. Okay. It's one of those kind of planes, not one of those kind of planes. The bottom of the new solid is a regular hexagon. Okay, because it's a regular hexagonal prism. That's fine. They kept the same bottom. Not A. A is down here. A, B, C, D. It depends on where they cut. That makes the U and the V that we can see. Okay. The 6 side faces are trapezoids perpendicular to A, B, C, to the bottom. Yeah, that's what right regular hexagonal prism means. The top is a hexagon that is not necessarily a regular hexagon. So we go U, V, W, X, Y, Z, and then back to U. It's not regular necessarily. I mean, if you cut straight across, it would be. It won't be regular in any other way, I don't think. Maybe if you cut so that you go from V to Y or something like that. But there is, while there's not regularity, there's still, because it comes from a single planar cut, there is still some, I guess, geometry going on there that we'll probably have to exploit. Of the 6 edges, let's move down a little bit. Of the 6 edges, AU, so that's this guy right here, BV, CW, DX, EY, so all the sort of heights. 3 have lengths 4, 7, and 10. So 3 of them, I don't know which 3. I mean, based on the picture, I would guess maybe UA is 4 because that's pretty short, but then again, they could all be sort of the highest, and then UA might be like 0.12 or something. I don't know. All right, but 3 of them are 4, 7, and 10. Okay. The largest possible value, I don't know what I just did there, but the largest possible value for the sum of these lengths is. And then we have a range of fun little possibilities. Okay. I'm not entirely sure how to get the scroll bar to go away. I don't know what I did. Doesn't really matter. Oh, okay, so it's a 3-dimensional geometry problem. You know my thoughts on these if you're in any way, shape, or form a regular viewer. You know I am not the best with these sorts of things. And, you might be in the same boat, or you might have something that you're particularly not good at. But it's always a good idea if you can identify a particular weakness. Like maybe you're just really bad at plain old trig or circle geometry, or it doesn't even have to be geometric. You might just be really bad with solving systems of equations. What you should never ever do is say, gee, I really hope that doesn't come up this year. Never do that. First of all, that's very defeatist. That's saying, there's no way I could get better for this. I mean, if it's the night before, then yeah, okay, say that. But hopefully you've identified your weaknesses, possibly by watching these videos and trying these contests. Hopefully you've identified your weaknesses ahead of time. When you find a problem, seek out similar situations, similar types of problems. If I'm bad at 3-dimensional geometry, I want to look through old contests, the geometry ones are really easy to pick out because they'll usually give you a nice little picture like that. Look at that. I fixed the scroll bar issue. They'll give you a little picture and you can say, aha, that's a 3D geometry problem. Seek them out, try them. Just, make up a whole contest's worth of them and try them and time yourself with them and see what you can do. Because, it's one thing to say, I'm bad at this. It's another thing entirely to say, I'm never going to get better, or I don't want to try to get better. Okay? So, if you're watching these videos, you probably want to do well on these contests. And identifying a weakness, like I've identified one of mine, is 3-dimensional geometry problems. That's just step 1. Step 2 is go find these problems and get yourself better. Step 3 might be read books and find theorems about them. Okay. So, I don't know which of these heights are going to be 4, 7, and 10. I'm going to give names to these heights rather than calling them AU and everything like that. I'll see if I can draw the picture. I don't want to draw this picture very many times. But ta-da. Okay, that was actually going pretty well until that last line there. Okay. So that's sort of the picture. You can see why I don't want to keep drawing this. We've got AU and, you know, BV. I'm going to give them the names. Just A will be the sort of height, the vertical distance from A to U. This will be B, C, D, E, and F. Now what we want is A plus B, the maximum possible value of A plus C, A plus B plus C plus D plus E plus F. I know one of them, one of A, B, I mean maybe more than one, but I know one of these values is 4, one of them's 7, one of them's 10, so at least we have 21. Okay, at least we've got 21. Now, one of the things I've learned when doing three-dimensional geometry problems over the year is to not get bogged down in the big picture. And I do mean that quite literally, as in, here's my big, I mean, it's a terrible picture that I drew. Theirs is much better, obviously computer generated, but the big picture, the three-dimensional solid, it's usually never a good idea to look at that. Now, you can look at it every once in a while for some inspiration, but usually what you're going to end up doing is looking at it from the side, or multiple sides, or from the top, or from the bottom, and trying to understand things there. Okay? That's usually the best way to go about these problems, is look at a side view, look at a top view, because we're much better with two-dimensional geometry than we are with three-dimensional geometry. Okay? So, I want to look at this and I want to say, okay, what I don't want to say is, three-dimensional geometry, where do I look? Start with some basics. Look at a side view. You know, they told me all the sides are trapezoids. So most of them are going to sort of look like this, and we might have, you know, A to U, F to Z. You know, that might be this guy over here. That's a trapezoid. Now, they haven't given me a whole lot of information. This would be A, this would be F. But I don't know what this length here is. And I don't know anything about the angles or anything like this. I do know I could chop this off here and make a right angle triangle. But and I can get 6 of these. And that might be useful in some way. What else could we do? Well, we could do sort of the top-down view. Now, when I do the top-down view, assuming I could draw a hexagon properly, I'm going to see a regular hexagon. Now, a regular hexagon is a nice thing to see, because regular hexagons have nice properties. You know, they can be broken down into equilateral triangles. I know all these sides are the same length, so, you know, whatever AF is here, it's going to be the same as AB. It's got internal angles of 120 degrees. But for this one especially, when I look down, I see A, but U is sitting right on top of A if I'm looking straight down. And so whatever U, V, all the way up to Z is, whatever that hexagon is, when I look straight down on it, it looks like a regular hexagon, the way things have been sliced. Now the question is that helpful in some way? You know, A, B, C, D, E, F. I don't think the 120 degrees from B, A, F is going to help. Just because I feel like we might need, we need to take a look at the sides themselves. And so the 120 degrees spanning between two sides isn't going to be the most useful. But perhaps if I chop it in half, I can get something with these 60 degrees. And as I think this is one of the first or second thing I remarked, is that you can chop this up into a bunch of equilateral triangles. Now, I don't know if that's, I don't think that's going to be particularly helpful. It is sort of involving this midpoint, this center point here, but you know, that'd be here, and I feel like the fact, like, knowing that these are all equilateral triangles might help in some sort of slope argument, but, well, it's a single planar cut. And so, if I project these equilateral triangles upwards, that doesn't do anything, really. Get to this point. So what I'm doing here is I'm taking these equilateral triangles and I'm sort of, imagine I were shining a flashlight down here. And so these lines are being projected up here. I think I have to, like, I think we need to use the fact that it's a single planar cut. And that might not be the most comfortable thing for people. But parallelograms, I believe, project up to parallelograms. And so maybe this midpoint up here is useful after all. We've got U, let's call him T, and call the midpoint down here G. I think, I think because ABGF is a parallelogram, that will project up to UVTZ is also a parallelogram, because it's a single planar slice. So, just trying to think, is that necessarily true? Oh, what have we got down over here? This is me just not knowing 3D geometry very well. But I think, yeah, and then, so that's a connection. So UVTZ is a parallelogram, parallel line symbol. But then I'm going to have a bunch of other parallelograms too, aren't I? I've already used purple. The question is, I mean, this is true, but is this helping me in any way? Well, again, because it's a single planar cut, like somebody came along and just sort of ran a piece of paper through my hexagonal prism, this should be a straight line from V up to Y. And it will be yeah, okay. So because this is a parallelogram, that tells me UZ is parallel to VT. Similarly, the redder parallelogram, uz is parallel to vy, therefore, or sorry, ty. Therefore, vy is a straight line. But not only that, because it's a parallelogram, these are the same length. Therefore, t is the midpoint. So it's not just the midpoint in terms of projecting upwards. It is, in fact, the midpoint of this line and this line and this line. Am I going to be able to prove that this is a regular hexagon? No, surely I can't. Could I? I'm going to draw another picture. I'm not going to draw as much as of the prism, but what I want to do is does this have to be so they all pass through T, that's fine. It's like I shone a light through the end and this whole thing was sort of glass. We got U, V, Y, Z, W, and X. Now, let's use a little color. I can show U, V, and ZT, because it's a parallelogram, these guys are the same. And so is TW. Again, parallelogram. And that would show, and then more parallelograms would show that XY has to be the same length. But I think we're gonna have, yeah. There's no, I don't think I can show it's equilateral, but I can at least show this property using parallelograms. And once again, I'd like to remind you, the parallelogram stuff is coming because we're sort of projecting parallelograms onto a single plane. So the parallelogram property still gets projected as well. This wouldn't work if it wasn't a single planar cut, but they gave us that, so that's fine. Okay, so what in the world can this tell me? And why do lines keep appearing in the corners? So T is the midpoint here, but isn't it also sort of height-wise? It's got to be in the middle. Imagine these were all y coordinates. If T is the midpoint, it's going to have the midpoint of it's going to have the middle y coordinate. That's E. We'll call this G. So that means that G, my length GT, is going to be 1/2 B plus E. But by the same token, it's also 1/2 A plus D. And it's also 1/2 C plus F. That is to say, 6G, if I multiply all these by 2, is going to be the same as A plus B plus C plus D plus E plus F. And that's the thing I want to maximize. Interesting, interesting. Okay. So that's fine. So the thing I want to maximize would be a quick calculation away if I can figure out what G is. And now, depending on whether, you know, like B is 4 and E is 7 and maybe F is 10 or something like that, the placement of my 4, 7, and 10 will affect what G can be, and therefore what 6G can be. Now, before I move on and start seeing how do my choices of A, B, like how does 4, 7, and 10 actually affect it, how can I calculate G? So I've got one way. If I know two opposite heights, G is just the average of those. But there are other possibilities. What if U is one of the lengths, V is another, and W is another? Can I figure out G from there? You know, if I know A, B, and C, So I guess what it is I'm about to assume knowledge of three of the points, or three of the heights, I guess. If I know any opposite pair, and then it doesn't matter what the other length is, I can figure out what G is. But what happens if I am told three adjacent ones? Or there's at least one other possibility. If I'm told three non-adjacent ones. And is there any other possibility? Because these formulas will handle this. I'll figure out G, and then I'll figure out what 6G is. But what if it's this case or this case? And are there any other cases? So here's none of the points being adjacent. Here's all three of the points being adjacent. Here's only 2 points being adjacent. So yeah, that works. Okay. So can I get a formula for G in terms of just A, B, and C? Can I get a formula for G just in terms of A, C, and E? Those are the remaining two cases. So, and then we can start making some assumptions. Okay. So I'll just mark this case off as done. I'm good if I know that. Okay. Just average the opposite ones. But what if I know just three adjacent heights? Maybe A, B, and C. Okay. I know A, I know B, I know C, and I want to figure out this length G. Or, so it's entirely possible I don't need to always figure out G, it just, and I will have to figure out D, E, and F, but that 6G formula is really nice. Okie dokie. So, using the power of parallelograms. So, I think whatever formula I get for this case, I can just tweak it a little bit as saying A is E minus 2G or something like that. But, yeah. I feel like it would be the average. I feel like G would have to be the average if it was sort of the case where it's those three. Anyway, I don't necessarily know, but okay. So, I want to use parallelograms. So there's this parallelogram with the A and the C quite nicely. So I think if I focus on this parallelogram here. Okay. So going from B up to A is the same as going from C up to G. So G minus C. So the difference in height there as a trapezoid is the same as the difference in height here as a trapezoid because these things are parallel. So G minus C is A minus B, so then G is A minus B plus C. So that's if the three of them are different. And of course this is assuming A is greater than B. If A were less than B, it would just be a simple tweak. It would be C minus G is B minus A. Again, parallelogram, but now we're going from B down to A. And so G would be A minus B plus C still. Okay. So as soon as I know three of them, it's just add the two outside ones and then subtract the middle one, whatever it might be, and then I'd multiply that by 6. Okay, now I think the previous two cases can combine. So what if it were, I am assuming my lengths, my heights are adjacent. our adjacent columns or pillars. So I know G is A minus B plus C. No. A, B, C. But I want it in terms of F, B, F, and D. Well, G minus A is the same as D minus G. And G minus C is the same as F minus C. Again, or F minus G. Again, just doing some parallelogram work. Or sort of straight line stuff. Straight line trapezoids, I guess. Yeah, same difference there. So I can replace A with 2G minus D, and I can replace C with 2G minus F. So in that case, G is 4G minus D minus B minus F. Or that is to say, 3G is B plus D plus F. So G is the average of them. Ah, cool. Intuition pays off. Okay. So now, we've got our cases worked out. There isn't anything else. So now, if we know two opposite ones and an adjacent one, the opposite ones could be a height of 4 and 7 could be opposite. 4 and 10 could be opposite. 7 and 10 could be opposite. G is the average of these. So G in this case would be 11 over 2. G in this case would be 7. G in this case would be 17 over 2. 6G in this case would be 66 over 2, which is 33. 6G in this case would be 42, which I think is the smallest answer we're given. And G in this case would be 3 times 17, 51, which I think is another one of the cases. Yeah, 51B. Okay. Now, what if I know 3 of them together? It doesn't matter. G is just the... So the question is, what's the middle one? Okay. So we could have A, B, and C. B will be the middle one. We could have 4, 7, 10. Technically, we could have 10, 7, 4, but that's just a mirror case, so I'm not going to list that. So we could have 7 in the middle. We could have 4 in the middle. We could have 10 in the middle. I'm not entirely sure this last one here is possible, but it doesn't matter. Okay, so what would that be? So 14 minus 7, so G is 14 minus 7, or 7 again, and so 6G is 42. Here we'll have 17 minus 4, which is 13. 6 times 13 is 78, which I think was... Is that D? Yeah, it's D over here. Okay. And then this one here is 11 minus 10, which is 1. Maybe it was possible. Oh yeah, I guess if I'd picked the highest thing, and then it starts to go smaller. So 10 all the way up here. We have much shorter things. Okay, so and then 6G would be 6. And then my final case, if none of the columns that I know are touching, and it was just the average. So, and it doesn't matter what order, so G is 4 plus 7 plus 10 over 3. So that's 21 over 3, which is 7, and once again, that 6G is 42. Now, 42 came up a whole lot here. Doesn't really matter. We're just going with the biggest one, and the biggest one I found is 78, which would give me an answer, as I just said, of D. Now, This really relied, I guess the way I did it, really relied on these parallelograms. That a parallelogram from one plane projected onto another plane. Sort of like, imagine that they were sort of see-through lines and you flashed a light and it projected them up. That they're still parallel. And that's, I mean, the geometry, it's veering into sort of vectors, which are not a grade 11 thing. In some places, they're not even a grade 12 thing. We do them in university, but university math shouldn't be brought to bear on a high school level contest. I think you could probably replicate some of what I've said about parallelograms with a lot of trapezoid work. You know, get that middle post there, that little G height or column, and then do some side view trapezoid work. I think that might help. Other things to just double check on with the question is, are there other cases? I've convinced myself there aren't other cases. But if I've missed a case, maybe I can get the, what was that bigger number? 91. Okay. So, maybe there is some way to get 91. But I don't think so, because I can't think of another case. Either all 3 columns that I know are together, 2 columns that I know are together, or 1 column that I know is together. Or none of the columns that I know are together. And yeah, so if we have 2 columns that we know together, the other column is either here or here, and it must be opposite one of them. Doesn't matter which one. We covered all 3 of those possibilities. So that wraps up the question, I guess. I'd be interested to hear if anyone else had a different way to do this. Not just because I'm a little shaky on the parallelogram explanation I gave, but just because, as I've mentioned, I'm not good at 3-dimensional geometry, and if you had another way to do it, I'm all ears, because I would love to get better at the stuff that I'm bad at. Okay? And if you've got a mindset where you want to go far in these contests, and you're bad at 3D geometry, you want to hear other solutions too. You want to know other ways to approach these problems. Okay? And then maybe in the future they're less scary. Alright, but that's going to do it for the 2008 Fermat paper. Up next will be the 2008 Hypatia, which is the grade 11 written paper. And if you're interested in any of that, I will see you for that when I post those videos. Until then, take care. Have a wonderful day.